Hello guys, this is section 2.3, Projectile Motion. It is the most important section in a kinematics because it includes a combination of the two motions, vertical, that is uniformly accelerated motion due to gravity, and horizontally, it is constant motion. To make it easy to understand projectile motion, we're going to review what we learned already before a vertical motion or motion at a y-axis under gravitational acceleration. We call it uniformly accelerated motion. Now let's have a ball tossed upward with initial velocity of 39.2 meters per second. Why did we choose 39.2? You're going to see later how that velocity will change after 4 seconds. So let's choose that level of the launching the ball vertically at the 0 level. Now, using two formulas, final velocity on y-axis is equal to initial velocity on y-axis plus ay delta t. We can calculate velocity each second. And using this formula, delta dy is equal to v initial y delta t plus half of the ay delta t squared, we can calculate position after every second. Let's start. So it starts with a 39.2 meters per second, and after 1 second is going to change to 9.8 meters per second is the gravitational acceleration. So that means that 39.2 up plus minus 9.8 meters per second times 1 is going to be 29.4 meters per second. And using other equation of displacement, you're going to see that is 39.2 meters per second times 1 second plus half of the minus 9.8 meters per second square times 1 square, 1 second square, which second square and second square cancel, and you're going to get 34.3 meters. You can try that in your calculator to see how you get it. Then after 1 second, you're going to see that velocity will change from 29.4 to 19.6. Where this come from is going to change another 9.8 meters per second. But since the direction of the velocity is up and direction of the acceleration is down, that is going to slow down with a rate of 9.8 meters per second. And displacement, using the same formula, you're going to have 58.8. Now, after 1 second, you're going to have another 9.8 decrease, which will end up 9.8 meters per second using this formula. Then another second is going to be less than 9.8. That means 9.8 minus 9.8 is equal to 0. And displacement is going to be 78.4 meters, and you can easily calculate that by using 4 seconds as a time. So initial velocity is 39.2 times 4 seconds plus half of the minus 9.8 meters per second square times 4 seconds all squared. Then you're going to see that answer would be 78.4 meters. So take a look. At the beginning is going to slow down at the same rate, 29.4, 19.6, 9.8, and 0. However, displacement is going to be different because at beginning is going to be bigger velocity, bigger displacement. Then as the velocity decreases, displacement decreases, and it's going to reach at the point 78.4 meters, and that would be a maximum height. How do we know that is maximum height? Because in value of final velocity. Value of the velocity at that point is 0. So at this point, the ball will stop for a fraction of a second and is going to fall back down. Now I want you to remember those two numbers, 78.4 and 39.2, because ball from this point is going to fall right back where it started. So after reaching that height, or if you are at that height and drop the ball, which is the same thing, then the ball will undergo accelerated motion, vertically, uniformly accelerated motion. So let's label that as 0, 0. That is a start from free fall from that position. And then after 1 second, we know exactly what is going to happen to a velocity and to a displacement using those both formulas. For velocity is going to be 0 plus 9.8 meter per second down times 1 is going to be 9.8 meter per second down. For displacement, it's going to be 0 times 1, 0, plus half of the 9.8 meter per second down times 1 is 9.8 meter per second down divided by 2, it's 4.9 meter. Another second is going to be another change in velocity by another 9.8 meter per second down, which will make 19.6 meter per second. And then the displacement is going to be 19.6. And after 3 seconds is going to be another 9.6 increase. And displacement, using that formula for 3 seconds, you can plug that in a calculator if you want to try it, and is going to give you 44.1. And finally, after 4 seconds, it's going to reach where it started. It is going to be 39.2 meter per second, and the displacement is going to be 78.4 down from this reference level. So it's going to be exactly the reverse of if that you toss that ball upward. If you build position time graph, but this time with a 3 seconds reaching the maximum point, if you see that at a 3 second it reaches the maximum point where the velocity is 0, you're going to see that the velocity changes by 9.8 as displacement is changing in a different way. So it's going to increase and it's going to reach the maximum and it's going to fall down. How do we know that it's going to decrease? So from 29.4 is going to decrease for 19.6 and it's going to decrease by 9.8 meter per second. That's very simple actually. You can draw a tangent at that point and you're going to see the tangent is going to be less steep than before. And at the point 3 seconds when velocity is 0, so you're going to see that slope of the horizontal line is 0. That's what slope of that tangent represent velocity. And if you continue on the other side of that graph, so when the ball will fall down, it's going to be 9.8 meter per second downward, so minus 9.8 meter per second. And how do you know it? By drawing a tangent at that point, and then you're going to see that it's going to be steeper. That means that the magnitude of that velocity is going to be bigger, and we know it's going to be exactly 9.8 meter per second bigger, and is going to fall at the same level as it started with the same magnitude. Obviously, it's going to be a different direction, but the same magnitude. So it's going to be a symmetry. And by using that, you can derive position time graph. You can build position time graph from position time graph, and you can build acceleration time graph from velocity time graph. So you see that at the highest point, when it reaches velocity is 0, so that's why it has the shape of the straight line. And for acceleration time graph, Slope of the straight line is a constant. That's why the slope is graph is horizontal. So that's pretty much it. We already have done it before, so you know you can recognize that type of graph. Let's talk about projectile motion when the object actually is moving horizontally with a constant motion of 4 meters per second. So why is constant horizontally? Is because there's no reason to accelerate. There's nothing, air resistance is negligible, is in an ideal situation, so nothing is slowing down or speeding up horizontally. However, vertically, there's a gravity. It's always gravity. So that means that vertically is going to be exactly what we already learned in a free fall. It's going to be accelerated motion. Every second is going to accelerate exactly what is going to happen. So projectile motion is a complex motion between horizontal constant motion and vertical uniformly accelerated motion. And we can calculate position and velocity for each second based on a formula. We can calculate velocity on x-axis, which is going to be a constant one, it's not going to change. We can calculate velocity on a y-axis, which is going to be changing because of the gravity, with a rate of 9.8 meters per second down. Displacement is going to be calculating using the displacement formula as delta dx is equal v initial x delta t plus half of the ax delta t square. However, I just mentioned ax is 0 because there's no reason to accelerate. There's nothing horizontally to make that object speed up or slow down. In an ideal situation with no air resistance, this component will be omitted. You don't even see that component at all when you calculate constant motion. You're going to use only this part. For accelerated motion, you're going to use entire thing because acceleration is 9.8 meters per second square down. Okay, so after 1 second, what is going to happen? After 1 second is going to be velocity is going vertically is going to change while horizontally is not. It's going to change at a rate of 9.8 meters per second. And displacement, as we already did before, with a 0 times 1 times half of the 9.8 meters per second down times 1 square, which make 9.8 meters per second, divided by 2 is 9.8 meters per second square times second square and second square and second square cancel. That will make 9.8 meter divided by 2, 4.9. Horizontally is going to be V initial, which was 4 meters per second times 1 second, second and second cancel, then it's going to be 4 meters. Now after 1 second, it's going to be pretty much the same change horizontally, another 4 meters, and vertically is going to be 19.6 meters. And you can calculate it using this formula for 2 seconds. So 0 times 2 is 0. Half of the 9.8 meters per second down times 2 in the power of 2 is 4. 4 divided by 2, 2 times 9.8, 19.6. And we can do that for 3 seconds. And you see that horizontally is going to change another 4 meters. And velocity is going to change another 9.8 meters per second down. And displacement, you're going to use that formula to calculate it. And the last one would be, again, it's going to reach 39.2 with a displacement of 78.4. While horizontally, it's going to be another 4 meters. And guess what? You already are familiar with those two numbers, right? 78.4 displacement and 39.2 after 4 seconds. as a final velocity on a y-axis. So, with other words, we can say that vertically is going to be exactly like that horizontal component doesn't exist at all. So they are totally independent from each other. The only thing that they have in common is time, 4 seconds, 3 seconds, 2, 1, 0. That means time of fly, time of motion. Now we are going to see the projectile motion with a faster horizontal motion. It was 4 meters per second, now it's 6. And let's see how that motion will look like. After 1 second, it's going to be 6 meters because 6 times 1 second is going to 6. So horizontally is going to be a simple formula as we already mentioned. So what about vertically? Vertically is not going to make any change at all because that's the same gravity. And after 1 second, the velocity is going to change at the same rate, 9.8 meters per second down with a y-axis. And displacement is going to be exactly 4.9 meters down. After another second, although horizontally is going to change by another 6 meters per second, from 6 to 12, vertically is not going to make any difference as before, so rate of change is going to be continuing for velocity at 9.8 meters per second per each second. Now it's going to reach 19.6, and the displacement using that formula is going to be 19.6, and you already have seen that before. And after 3 seconds, it's going to reach another 9.8 meters per second velocity down, and displacement is going to be 44.1 meters, while horizontally it's going to be at exactly a constant motion, exactly the same change, another 6 meters horizontally. So the last one would be after 4 seconds, it's going to be another 9.8 meters per second increase. That will make final velocity after 4 seconds 39.2 and displacement 78.4. Guess what? Is exactly that displacement and velocity, vertical displacement and vertical velocity that we already seen as a free fall or at the projectile motion with a 4 meters per second. So that makes us think that those two motion will be exactly the same vertically because they are under exactly the same gravity moving under. However, horizontally is going to be a bigger displacement, as you see is more stretched, that trajectory. If the ball is moving at a certain direction in a deep space, when there's no gravity there, what is going to happen? This ball is going to continue to move at a straight line at a constant velocity because there's no reason to change either direction or magnitude. However, we are talking about on Earth. So there is gravity acting on it. So that gravity is going to affect a vertical motion of that object the same way as before. So that means that we chose two components just for illustration, and we chose those components to be out of scale. So vertical one is plus or positive 19.6 meters per second, and horizontal one is going to be 4 meters per second. Now, what will happen after 1 second? After 1 second, the ball is going to displace downward with a 4.9 meter, and velocity is going to be affected exactly with a 9.8 meter per second downward. So velocity from 19.6 positive direction is going to be minus 9.8 is going to be 9.8 meter per second. Now, next one after 1 second, again from the position that there's no gravity. This motion is going to be pulled down, and the velocity was plus 9.8 is going to be affected by the same rate, minus 9.8 per second. So that means 9.8 meter per second minus 9.8 is going to be 0 meter per second. So we're going to have only x component while the y component is 0. After 1 second, it's going to be pretty much the same thing. Displacement from that no gravity line is going to be displaced by 44.1, and you can calculate it using that formula. And velocity is going to be affected again by gravity by 9.8 meter per second downward, which makes minus 9.8 meter per second. So after is going to be, you see that symmetry for 1 second and 3 seconds. Velocities are going to be up 9.8 meter per second, and velocity here is going to be down 9.8 meter per second, while the horizontal component is not going to be changed. So after another second, from that non-gravity line, the ball is going to be displaced exactly 78.4, and remember that number, it's very common now, it's very well known, and the velocity is going to be affected by minus 19.6 meter per second. So if you see that value at this point is exactly symmetrical with the value of this point when we have 19.6 positive and we have 19.6 negative, and horizontal is the same, so the magnitude of final velocity is the same. If we analyze two types of motion, vertical free fall and projectile motion, you're going to see that they undergoes under the same gravity. That means that the vertical component of both are going to be affected exactly the same because both of those are under the same gravity. However, horizontal component is going to stay exactly as it were, because horizontally this is not affected by gravity. So the object that you throw horizontally will experience the same vertical motion as the object that falls down in a free fall. Amount of time it takes for a projectile to complete its motion is known as the time of flight, and it is exactly the same for a free fall and for projectile motion. So both motions are under the same gravity, and they are going to reach the ground exactly the same way. And displacement, it is pretty much the same. If you take a slow motion picture or picture video or a picture for every fraction of seconds, you're going to see the position of the ball in a free fall or in a projectile motion vertically is going to be exactly the same. So after a certain second, it's going to be exactly the same for ball to be displaced vertically under the same gravity. The motion of the projectile under gravity is called projectile motion. The trajectory of the projectile is called parabola, and parabola is a graph. Position, position, graph. Not position, time, graph. Position horizontally and position vertically. So, in order to understand the parabola, the shape of the parabola, you can analyze the initial velocity. And you can resolve initial velocity in two components, on x component and on y component. Y component is going to affect maximum height. So at a maximum height, y component is going to be 0. Y component of velocity is going to be 0. So it is the point where that object will stop for that fraction of a second and is going to fall back. Now, x component is going to affect what we call horizontal distance traveled by a projectile, as we know it to be called the range. Range is between start and end. Start horizontally and end horizontally. Now, vertically, sometimes parabolas have the same vertical displacement. So, for example, this parabola starts at 0 and end up at 0. It's a fully symmetric. However, there are other parabolas that may start at a certain point, at a certain vertical displacement, and is going to end up to 0 displacement, for example, in this case. However, range is the same, where the start horizontally toward where the end horizontally. Here's a gizmo. You can just try it at home. It is about actually shooting a monkey with a banana so they can, banana and monkey can meet in air. And the question is, where should we aim the banana cannon so the monkey, who is at the same time free falling, can catch the banana? Remember that it's an ideal situation where air resistance is negligible. So for a monkey it's a free fall, and for a banana is perfect projectile motion. So we can try it and you see that it is aiming exactly toward monkey, because both banana and monkey is going to be displaced from on a vertical direction equally, because both of them are under the same gravity. This part is very important. How to build and calculate elements of the projectile motion. We have an object that is moving at the initial velocity at angle theta with x-axis. We build x and y coordinate so that origin of that coordinate system to be where the start position is. Then we can draw a line which is a parabola so that v initial to be tangent at the start position. Since that v initial is not on x, not on y, we can draw two lines that are perpendicular to x, perpendicular to y from the tip of the v initial, and then draw its component, label it, and then we can calculate this component by making sure you use cosine for adjacent and sine for opposite. In this case, adjacent is v initial x and opposite is v initial y. Next step would be take a look of most important points. Start point, the point where it reaches the maximum, the symmetrical point, and the end point. Now, next step would be how to calculate the maximum height. We know that at maximum height, y component of velocity is going to be 0, while x component is not going to be affected at all. So we can use delta y maximum is equal v final y square minus v initial y square divided by 2ay. Ay is g, is minus 9.8 meter per second square. Next step would be time of flight. So it's a time that object is on air, in the air. So starting from the start point, reaching the maximum, coming back to the symmetrical point, and falling down to the ground. So vertically, it starts from this level, and we fall to this level. So that's why the vector delta dy start where the start position is toward ground. The direction is opposite of the positive, so that's why delta dy is negative. Now, since that involved delta dy, we can write a formula. Delta dy is equal to v initial y delta t plus half of the ay delta t square. Now, we can move this component with a t square at the front. We move v initial y delta t in the middle, and we move delta dy to another side of the equation. That becomes negative, and that is the form of the equation. Half of the ay delta t squared plus v initial y delta t minus delta y equals 0. Then this is exactly like the second degree equation when we have ax squared plus bx plus c is equal 0. And then to find x, or time in this case, we use quadratic equation minus b plus minus square root of b squared minus 4ac divided by 2a. Or it is another one that's already made. Delta t is equal minus v initial y plus minus square root of v initial y squared minus 4 of half of the ay times minus dy divided by 2 half of the ay. So then you can have two values. One is positive and one is negative. You are going to ignore the negative value because negative time doesn't make sense. And you're going to take only positive time. I want to draw your attention to sign of the delta dy. Make sure that is negative, and when you move to another side of the equation, that becomes positive. So negative and negative, that becomes positive. And another thing is, make sure that sign of half of the ay is half of the gravity, which is minus 4.9. And here is minus 4.9 as well. So there are a few things that you may make mistake. So just by being careful, you're going to avoid that, because time is very important. It's used on a range as well to calculate horizontal range. So if you make mistake here, it's going to be carried over on a range calculation as well. Next step would be calculate final velocity. We know that final velocity on x component of final velocity is the same as x component of initial velocity because it never changes. So now we just need to calculate y component of final velocity, and we can use y component of final velocity using a fourth equation of kinematics is equal to square root of v final y squared minus 2ay delta dy. You make sure the signs are very important. Negative sign for ay and negative sign for delta y, which makes that positive, and positive sign for v initial y. So you can follow the signs. V initial y positive, d delta dy negative, and g negative. And then the next step is, as you have two components, v final x and v final y, you can draw v final and then calculate using Pythagorean theorem, and then using tan negative 1 to calculate angle phi for that final velocity, and that is below horizontal. The last step would be range. The range is from start to end, but in a horizontal point of view, horizontally. So then, since that horizontal motion is a constant motion because this component is a constant, then it is a simple calculation. Delta dx is equal v initial x delta t. And that's it about calculating projectile motion. And just to take a look on that animation as well, it's very clear that y component of velocity decreases, and then at the maximum point becomes 0, and when it falls down it increases because of the gravitational acceleration, while the horizontal component of acceleration never change, because there's no reason to change. Horizontally nothing is going on, no air resistance, no any slowing down or speeding up. And that is what you need to calculate projectile motion elements. Let's do some practice problem involving projectile motion. A soccer player kicks a soccer ball with a velocity of 9.4 meters per second at the angle 60 degrees above horizontal. Determine the ball's time of flight, delta t. So we have v initial 9.4, we have angle 60 degrees, and time is required. So in order to calculate time, we need to use delta dy is equal to v initial y plus half of the ay delta t square. So that means we need y component of initial velocity. So v initial y is equal to v initial times sine theta. That is equal to 9.4 times sine 60 is equal to 8.14 meters per second. So delta dy is equal v initial y delta t plus half of the ay delta t square is equal 0, because it starts and ends to the same horizontal level. That means that vertically it does not displace between start and end. So it's 0. Delta dy, or change on vertical position, is 0. So we don't need a quadratic equation. We can factor delta t, and we need to use delta t equals 0, which is the start point, and v initial y plus half of the ay delta t is equal to 0. From here, we can solve for delta t, which is 2 times minus v initial y divided by ay, or now you plug the numbers, 2 times minus 8.14 divided by minus 9.8. And if you do that calculation, that will give you 1.66. To calculate horizontal displacement delta dx, you need v initial x. So we can calculate that v initial x is equal to v initial cosine 60, which is 9.4 times cosine 60 is 4.7. Next step would be calculating a horizontal displacement, which we can use the formula that we use for any accelerated motion. So delta dx is equal to v initial x delta t plus half of the ax delta t square. However, you don't really need that second component because ax is 0. There is nothing horizontally to make it. So that is component here is 0, and the next one would be delta dx is equal v initial x delta t, and if you plug those numbers, 4.7 meters per second and 1.66 second that we already calculated at point A, we can get delta x is equal to 7.8 meter. The next one is maximum height, is where the final y component of final velocity is 0. While initial we know already is at 8.14, and we know final velocity on a y-axis is 0, then we are ready to calculate what would be a maximum height. So 0 minus 8.14 squared divided by 2 times negative 9.8. Negative up and negative down will make it positive. So the displacement is on a positive direction. and we do a calculation and we get 3.38. Here's another projectile motion practice problem. A helicopter flying at a velocity of 25 meters per second at an angle of 37 degrees above horizontal drops a supply package from 100 meters directly above the raft. How long is the package in air? So let's start what is given, what is required. We have V initial 25 meters per second. Angle theta is 37. Delta dy is negative 100 meters. Remember, the delta dy start from where it starts and end to the ground. That is direction, is negative because positive is up. And delta t is required. So first we need to get those components. V initial y is equal V initial times sine 37, 25 meters per second times sine 37 is equal 15 meters per second. And then you can calculate delta dy is equal V initial y delta t plus half of the ay delta t square. So then we can rearrange this equation by moving delta t square in the front and delta t in the middle, and move delta dy on another side of the equation. That becomes negative. So that is going to be half of the ay delta t square plus V initial y delta t minus displacement, vertical displacement y equals 0. Next step would be using a quadratic equation. So minus b plus minus b squared minus 4ac divided by 2a. Then we can plug those numbers. Remember, do not use V initial. You have to use V initial y. That is a common mistake people do all the time. Instead of using V initial y, they use V initial, and the answer would be wrong. So delta t is equal minus 15 meters per second plus minus square root of 15 meters per second square, all square, minus 4a, which is minus 4.9, and delta dy, which is minus 100, that means plus 100, divided by 2 minus 4.9, which is a. That is giving you two values. If you plug those values in the calculator, you'll get two answers. One is negative 3.24 second, and one is positive, is 6.3 second. Obviously, you're going to get positive value because time, negative time doesn't make sense. Here's a practice problem. A golfer drives a golf ball from the top of the cliff 30 meters above the ground with an initial velocity of 22 meters per second at an angle of 50 degrees above horizontal. Determine the ball times of flight, delta t. What we have is a initial 22 meters per second. Is theta, angle, is 50 degrees above horizontal. Delta dy minus 30 meters, and delta t is required. Let's get those two components of V initial. V initial y is V initial sine 50, which 22 times sine 50 is 16.85, and V initial x is 22 times cosine 50 is equal 14.1. Delta dy is equal V initial y delta t plus half of the ay delta t square. Let's plug what we have. We have minus 30 is delta dy. 16.85 is V initial y, and minus 9.8 meters per second square is ay or g. Now, we can rearrange this equation by moving the half of the minus 9.8 meters per second square delta t square in front, because that's delta t square. So half of 9.8 is 4.9 delta t square plus 16.85 delta t. Then when we move minus 30 to another side of the equation becomes plus 30. That is equal to 0. Then we can use minus b plus minus square root of b squared minus 4ac divided by 2a. The same thing, we plug those numbers in that equation, second degree equation, to find two values, one positive, one negative. We ignore the negative value and we can keep that only positive value, which is 4.73 seconds. Now we can determine the range or horizontal displacement. We have v initial 22 meters per second. We have delta t that we just calculated, 4.73 seconds, and delta dx is required. We already have calculated this. V initial x is equal 14.1 meters per second. And then we can have delta dx is equal v initial x times delta t. We have both. 14.1 is v initial x and 4.73 is delta t. And then we can calculate it, delta dx is equal 66.7 meters. Determine the maximum height from ground, delta h. So delta h is delta y max plus delta y. So let's start what we have. We have v initial y 16.85. Angle is 50. Delta y max is what we need to calculate first, and delta h we calculate after, just adding delta dy. So we know at the maximum point, at the maximum point of the delta y max, that is when v final y is 0. So that's why v final y is 0. That will serve us to solve for delta y maximum, which is 0 minus v initial y, already we have it, 16.85 meters per second, all in a power of 2, divided by 2 times negative 9.8 meters per second square. And if you plug that in the calculator, you'll get 14.5. And then you add 30, which is delta dy, and we'll get 44.5 meters. Next step and final step is to get a final velocity before it hits the ground, magnitude and direction. So what do we have? V initial y is already calculated, 16.85. V initial x, 14.1. Delta dy minus 30. What we're looking, final velocity with angle, with that direction. So in order to calculate final velocity, we need two components. So in order to calculate final velocity, we need v final x, which is the same as v initial x because they never change, and we calculate v final y. So you don't need to calculate v final x because it's already 14.1. Then we can calculate v final y, which is a v initial y plus 2a y delta dy. We have everything to calculate it. So v final y is the square root of v initial y squared plus 2ay delta dy, 16.85 square plus 2 times negative 9.8 times negative 30. And then you plug those in the calculator and you get 29.53 meters per second. So after getting this, we can calculate angle. And angle is tan negative 1 of opposite over adjacent. And opposite is 29.53, we just calculated. And adjacent is the small x component, is 14.1, and angle is 64.5 below horizontal. Angle phi. Then v final is equal square root of v final x squared plus v final y squared is equal square root of 14.1 meters per second squared plus 29.53 meters per second all squared. Then v final is 32.7 meter per second, 64.5 degree below horizontal. This is the last practice problem for this lesson. A golfer sent a ball over a tree which is 3 meters high. This tree is 14 meters away from a golfer. The ball lands on a green at the same level from which it was struck after traveling a horizontal distance of 17.8 meters. If the ball left the club at 54 degrees above horizontal and landed 2.24 seconds later, what was its initial velocity? Now we have delta t is equal to 2.24 seconds. Angle is 54 above horizontal. Position of the tree, it is delta d1 x 14 meter, and delta x, which is a horizontal displacement or a range of the projectile, is 17.8 meter. V initial is unknown. Now, V initial, to find the V initial, we can draw its component. Then, you know the V initial x is already adjacent of V initial. So, in order to find V initial, we can find V initial x first because we do have the values, we have data for it. V initial x is the responsive for horizontal displacement. We do have horizontal displacement, the range, and we have a time. Since that is a constant velocity, it is easy to calculate. So V initial x is delta dx over delta t. It's a 17.8 meter divided by 2.24. That makes initial velocity, x component of initial velocity of 7.95 meter per second. Now, when we have adjacent of 54, we can calculate hypotenuse, which is V initial. So V initial is adjacent over cosine theta, which is V initial x over cosine theta. That is equal to 7.95, we just calculated it, divided by cosine 54. That is equal to 13.5 meter per second. That is initial velocity. Let's continue with the B. How high was the ball when it passes over the tree? What we have is a V initial x, 7.95 meter per second. We have a angle above horizontal, 54 degree. We have position of the tree, 14 meter. And what we're looking for is exactly the height of the ball up top of the tree. So in order to find that height, you need time when the ball arrives here. But that will help the horizontal displacement is easier to find the time because it's a constant motion. So we know the position of the tree. We know the x component of initial velocity. We can find time. So time is equal delta d1x divided by V initial x. 14 divided by 7.95 will give you 1.76. So once you have time, we can calculate displacement. Delta y of the tree when the ball is right above the tree is equal V initial y delta t1 plus half of the ay delta t1 square. But we don't know V initial y. But take a look. The V initial y is the opposite of the angle and V initial x is adjacent. So know that tan is opposite over adjacent. That tan theta is equal V initial y divided by V initial x. We can solve for opposite, which is V initial x times tan 54 degree will give you 10.9 meter per second. Then we go back to that equation and we can plug numbers. V initial, it is already, y is already found is 10.9 meter per second. Time is 1.76 second. G, or AY, is minus 9.8 meter per second square. Time is 1.76 second, all in the power of 2. And we plug those in the calculator and we get 4 meter, which is well above 3 meter high. So the ball will pass over the tree and is going to land successfully on that green. So this is it about projectile motion. I hope you learned. I hope you enjoyed it. So see you next time.